Nobody passes organic chemistry. It just doesn't happen. You study for weeks. You memorize stuff. You draw hexagons until your hand cramps up. You fail. You cry. You draw more hexagons. And here's the thing. The reason Orgo destroys everyone isn't because it's impossibly hard. It's because nobody ever explained why any of it matters. So that's what we're doing today. All of organic chemistry. In 18 minutes. Let's go! Okay, so first question. Why carbon? N? Like, out of all 118 elements on the periodic table, why is carbon the one that gets to be the star of an entire branch of chemistry? Why not sodium? And why not oxygen? N. Why is it always carbon? N. Here's why. Carbon has 4 electrons in its outer shell. 4. And it needs 8 to be happy. That's just how atoms work. They're basically desperate to fill their outer shells. Like people collecting stamps, except the stamps are electrons, and the consequences of not collecting them are molecular instability. So carbon needs 4 more electrons, and the way it gets them is by bonding with other atoms. 4 bonds. Every time. That's carbon's whole personality. Now here's where it gets interesting. Most elements are picky. Oxygen mostly bonds with 2 things. Hydrogen bonds with 1 thing, and that's it. Hydrogen is boring. Hydrogen has no ambition. But carbon? Carbon will bond with almost anything. Other carbons. Hydrogens. Oxygens. Nitrogens. Sulfur, phosphorus, halogens. Carbon does not discriminate. Carbon is the most socially active atom on the periodic table. Carbon is the golden retriever of chemistry. Just vibing, making bonds, being friends with everyone. And because carbon will bond with other carbons, you can build chains. Long chains. Branched chains. Rings. Rings inside rings. Carbon chains are like Lego sets. The same basic pieces, but you can build basically anything. A candle. A steroid. A strand of DNA. Your own body. All carbon chains, just arranged differently. So organic chemistry is basically just what happens when carbon makes different shapes and what do those shapes do? That's the whole subject. But, and this is the part they don't tell you on the first day, the shapes matter insanely. One tiny change to the shape changes everything. The smell, the taste, the toxicity. Literally whether something saves your life or kills you. You've smelled vanilla, right? N. Vanillin. That warm, sweet smell. Vanillin is a specific carbon structure. Now here's a question. What if you took that exact structure and swapped out one group of atoms? N. Just one. Keep most of the hexagon. Just tweak the side piece. Do you still get vanilla? Nope. You get eugenol, which smells like cloves. Tweak it again? You might get something that your liver cannot process and will ruin your day permanently. Same basic skeleton. Wildly different molecule. The shape is everything. This is why organic chemistry exists as its own subject. It's not about memorizing elements. It's about learning the language of shapes. And like any language, it has an alphabet. In Orgo, that alphabet is called functional groups. A functional group is just a specific cluster of atoms attached to your carbon chain that determines what the molecule does. It's like adding different apps to the same phone. The phone, the carbon chain, is the hardware. The functional groups are the software. Different software, completely different behavior. And here's the part where most professors lose people. There are a lot of functional groups. Like, a lot. But here's the part professors don't tell you. You don't need to memorize all of them on day 1. You need to understand the logic behind them. Because once you get the logic, the rest of it clicks. So that's what we're building. The logic. We're going to go bottom up. We start with the simplest carbon structures, the ones with nothing interesting attached. Then we're going to add stuff to them, one functional group at a time. And every time we add something, we're going to look at what changes. By the end of this video, you are going to look at a chemical formula and feel something. Not panic. Understanding. Or at the very least, like 40% less panic. That counts. But before we get there, we need to talk about the hexagon, because you've seen it. You've drawn it. You've probably drawn it so many times that it shows up in your dreams. The hexagon is everywhere in organic chemistry, and most people have no idea why. Where does the hexagon come from? And why does it change everything? N. The hexagon. Okay? Deep breath. The hexagon in organic chemistry is benzene. 6 carbons bonded together in a ring, with 1 hydrogen on each carbon. And if you just look at it, it seems fine. It seems normal. 6 carbons holding hands in a circle. Cute. But benzene is not normal. Benzene is genuinely weird. And the weirdness is the whole point. Here's the question. If each carbon in that ring has 4 bonds, and it's bonded to the carbon on each side of it, plus 1 hydrogen, that's only 3 bonds. Where's the 4th? N? You've got 4 hands, 2 are holding neighbors, 1 is holding hydrogen. What's the last hand doing? N. This is where things get weird. The 4th electron from each carbon, all 6 of them, doesn't belong to any single carbon. They pool together. They form a cloud. A delocalized electron cloud that floats above and below the entire ring, shared equally by all 6 carbons. No single owner. Communal electrons. Now why does this matter? And because those shared electrons make benzene crazy stable. Like, unusually stubbornly stable. Most molecules want to react. They see another molecule and they're immediately trying to grab electrons, swap atoms, do something. Benzene looks at that offer and says, "No thank you. I'm good. My electrons are already perfectly happy. Don't touch them." This is called aromatic stability, and it shows up everywhere in chemistry. Aspirin is aromatic. Caffeine is aromatic. The compounds that make coffee smell like coffee are aromatic. The neurotransmitter dopamine, the one your brain releases when something feels good, has an aromatic ring in it. You are, at a biochemical level, experiencing aromatic stability right now by watching this video. That's not a metaphor. That's literally what's happening in your neurons. Okay, but here's the awe moment. Ready? N? Actually, sit with this one. Wow. There are estimated to be around 10 million known organic compounds. 10 million. And they are all, every single one, built from essentially the same set of atoms. Carbon, hydrogen, oxygen, nitrogen, and a handful of others. That's it. Life, in all of its incomprehensible complexity, is basically remix culture. The difference between a protein that builds your muscles and a toxin that destroys them is not different atoms. It's different arrangements. Different shapes. Different functional groups attached to similar skeletons. The universe figured out early on that carbon chains with functional groups were so versatile you could build literally everything out of them, and then it just did. You are 10 million possible molecules worth of, what if we tried this arrangement? Take a moment. Okay, moment over. Back to functional groups because we have ground to cover. So far, a plain carbon chain with only hydrogens attached is called an alkane. Ethane, ethane, propane, the stuff in gas stoves. Boring, stable, just burns. Not very reactive. Think of an alkane as a plain white t-shirt. Perfectly functional, 0 personality. Now, start swapping things in. Replace 1 hydrogen with a hydroxyl group that's an oxygen with a hydrogen hanging off it written as OH, and suddenly you have an alcohol. Ethanol, specifically, if you're working with a 2-carbon chain. The stuff in drinks. Same basic carbon chain, just added OH. Now it's water-soluble. Now it interacts with biological systems in specific ways. Now it tastes different. Now it has entirely different chemistry. Okay, so what if instead of adding OH, you added a carboxyl group? N. That's a carbon double bonded to an oxygen and also bonded to an OH. You get a carboxylic acid. Acetic acid is vinegar. Formic acid is what ant bites inject into you. Fatty acids are what your body stores energy in. All of them. Carbon chain, carboxyl group on the end. The carboxyl group is just doing its carboxyl thing, being acidic, donating protons, living its life. And here's the pattern that Orgo is always trying to show you, but textbooks somehow make invisible. Every functional group has a personality. Alcohols are social. They hydrogen bond with water, which means they mix, they dissolve, they play well with biological systems. Carboxylic acids are sharp, they're acidic, they donate protons, they're reactive in specific ways. Amines, nitrogen-containing groups, are basic, they pick up protons, they show up constantly in drugs and neurotransmitters because nitrogen interacts beautifully with biological receptors. Esters smell like fruit. Ethers are weirdly stable. Ketones are in nail polish remover. You've smelled all of these. You've consumed several of them. You've literally had these functional groups inside your body. Here's the thing that should reframe everything. When a pharmacist says this drug has a half-life of 6 hours, they're describing what functional groups do to a molecule in your liver. When a chef says this dish has a complex flavor profile, they're describing dozens of volatile organic compounds hitting your olfactory receptors simultaneously. When a perfumer creates a scent, they are doing applied organic chemistry with their nose. Organic chemistry is not the thing you learn so you can get into medical school. Organic chemistry is the operating system of biological reality. Everything else is just the interface. But wait. If functional groups are just atoms attached to carbon chains, why is it so hard to draw them? N. Why does every Orgo student have nightmares about hexagons and arrows? N? What are all those arrows even doing? N? The arrows. Okay. This is where people lose it. In organic chemistry, those little curved arrows everywhere are not decoration. They are not the professor just messing with you. Each arrow represents the movement of electrons. Specifically, a pair of electrons moving from one place to another. The arrow starts where the electrons are and points to where they're going. That's it. That's the whole arrow system. But here's why it feels impossible. Electrons move in patterns. Predictable, logical patterns, but only if you already know the patterns. If nobody explains the patterns, you're just looking at a page full of arrows going everywhere, and it looks like chaos. It feels like trying to read a book in a language where you know all the letters but none of the grammar. The grammar of those arrows is reaction mechanisms. And a reaction mechanism is just the step-by-step story of how electrons move to turn one molecule into another molecule. Every single organic chemistry reaction, and there are hundreds, is just a variation on a small number of electron-moving patterns. Addition, elimination, substitution, rearrangement. 4 basic plots. Every Orgo reaction is one of these 4 stories, or some combination of them. If your professor taught you that on day 1, this subject would be 3 times easier. Instead, you memorized 40 reactions individually and cried. You're welcome, I'm telling you now. And those reactions, those electron stories, are what your body is running constantly. Right now, in your liver, enzymes are running substitution reactions to break down whatever you ate for lunch. In your cells, ATP is transferring phosphate groups in reactions that look exactly like what you practiced in lab. Your DNA replication machinery is doing addition reactions to build new nucleotide chains. You are a biochemical reaction mechanism, walking around, drinking coffee, watching YouTube. Here's the plot twist that will either make you love chemistry or existentially spiral. Ready? Wah! The rules of organic chemistry are the same everywhere in the universe. We know this because we've detected organic molecules in space. In meteorites, in interstellar clouds light years away. Amino acids, the building blocks of proteins, have been found in meteorites that crashed to Earth. The same functional groups. The same carbon logic. The same electron rules operating in the vacuum of space billions of years ago in a nebula that had never heard of medical school. Carbon doesn't care where it is. It just makes 4 bonds and keeps building. So when you ask why organic chemistry is worth understanding, it's not because of the MCAT. It's because carbon chemistry might be the reason anything alive exists anywhere. The universe seems to have a bias toward carbon-based complexity. We don't fully know why. We don't know if every planet with liquid water eventually gets organic molecules. We don't know if those molecules always, eventually, start copying themselves. We don't know if life is something the universe does on purpose, or just a really common accident. That is a genuinely open question. Scientists are actively fighting about it right now. And that question, is the chemistry of life inevitable, or are we a cosmic fluke? That's the question that organic chemistry eventually leads you to. Not, what is the product of this reaction? Not, name this functional group. The real question, the one sitting at the end of the whole subject, is, are we alone because life is rare, or are we going to discover that carbon chemistry makes life basically unavoidable? Did the universe build a machine for making living things, and are we just one output of that machine? And we don't know. We genuinely, scientifically, do not know yet. But here's what we do know. You understand organic chemistry now. You know why carbon is the star. You know that functional groups are just personality upgrades on a carbon chain. You know that benzene's electron cloud is why your coffee smells like coffee. You know that every reaction is just electrons following a script. You know that your body is running this chemistry in the background constantly, whether you passed Orgo or not. So next time you're staring at a hexagon on a page at 2 in the morning, surrounded by empty coffee cups, wondering why you chose this major... Remember, you're not just drawing a hexagon, you're drawing the shape that life uses to build itself. You're tracing the outline of the operating system of the universe. That's organic chemistry. And we still don't know where it ends.